Hello and welcome to any combo lords joining me. To anybody joining me in the future, note that for these live videos, I will now be putting on a little in the description and maybe a comment chapters or little clickable timestamps for different activities we'll cover. So anytime you miss one of these streams, or for people who don't care to watch them live, make sure to check out these live videos anyway and comb through the chapters and see if there's anything up your alley. And a few reasons why I decided today was a good day for another stream is that, for one, as we noted in our last stream, it is Squirrel Appreciation Day. And while that's a very silly holiday, there are squirrels running about my yard that I appreciate. And I saw some crazy squirrels this morning, so I was like, better be streaming in case the squirrels start going crazy back here again on their little squirrel routes or routes, depending how you pronounce that. And in the midst of our squirrel routes or squirrel routes, depending how you pronounce that, we'll also be looking at square roots, a similar sounding but very different conceptual thing. And that's because I've recently posted a short here about the square root of 1/2. An actually really interesting number with a lot of different ways we could write it. And so, whether or not you've seen the short doesn't matter. We'll go through an even more detailed version of that today. As for why does this have so many different ways we can write it and conceptualize it geometrically? There are ways in which we can show that this equals a bunch of other stuff algebraically, and ways we could show that same equality geometrically. So, first of all, let's think, what does it mean to take a square root of something? Well, when you stick this symbol on the outside of something, that's called the radical symbol typically, and generally refers to the principal square root. So we don't have to worry about the fact that square roots can have two answers with one of them being negative. We're going to ignore the negative one because this symbol, the radical, actually means you're allowed to just focus on the principal positive square root answer. So we're looking at what number, if we were to square it, gives us 1/2. And if you were like a kid, you might think, well, maybe a quarter, because you add a quarter and a quarter, you get a half. But if you square a quarter, you get something smaller than a quarter. That's getting you the wrong direction. Then you might think, well, maybe 3/4 or something, but it's not quite exactly that. And if we decode this a little more, we can note that this can be rewritten as the square root. And this is what the rain does to some of the whiteboards. This whiteboard got a little curvy from the rain. We could also rewrite this as square root of 1 over square root of 2. And we know the square root of 1 is 1, so we can get rid of that square rooty thing. So this is our first step. It's not necessarily the neatest form to have this in, but it is equal to 1 over the square root of 2. And 1 over something is a notable thing in math. It's the multiplicative inverse, known as the reciprocal. So this number, the square root of 1/2, could also be called the reciprocal of the principal square root of 2. But what else is it? Well, if we were to take this and then try and multiply the top and bottom of this fraction by something to rationalize the denominator, which some people are insistent that you always need your denominator rational. Not true. Sometimes it helps to have it irrational, but there are times where it helps to have the denominator be rational. So what we're going to do is see what it looks like in that case. The way to rationalize this would be to hit both the bottom and the top with a square root of 2. And we can multiply this by root 2 over root 2, because root 2 over root 2 is 1. So these collide into a 2, and these collide into a square root of 2. So that sends us to square root of 2 over 2, which is a more common way you might see this one written. These are both true, that these are both answers for what the square root of 1/2 is, but it's a little more common that you'll see it with the square root of 2 on top and the 2 on the bottom. Now, before we move on to some more of the really weird, interesting algebraic ways we could phrase this, let's think about what's geometrically going on. What is the square root of 2? And what is half of the square root of 2? Or what would it mean to be a reciprocal of the square root of 2? Well, kind of like pi has a really simple geometric context, we can say pi is the ratio of circumference to diameter, or could define it based on area and stuff. The square root of 2 lives in a square. A square's diagonal is the square root of 2 times longer than one of its sides. And so we're going to call these each 1 and call that square root of 2. But, ooh, Squirrel Appreciation Day. Was that a squirrel? Sounded like a squirrel. Got to be on the lookout because it is Squirrel Appreciation Day. So if we call this square root of 2, if you are worried that I'm defining this as my square happened to have sides of 1, we could have said x root 2. It is always root 2 times longer than the side, regardless of if it's a side length 1, but let's call it 1 to keep it nice and simple. So that's where it's hanging out, inside of what we could call, a little unit side length square. So what is this little shape that we get when we cut it in half? This little shape we get is often taught in school as something called the 45-45-90 triangle. Bad name, 2-degree centric. I know in my short that I posted about this, I did use degrees, because it turns out that these are equal to sine of 45 degrees and cosine of 45 degrees are also both equal to this square root of 1/2 thing. And I did put it in degrees in my short because I wanted more people to understand it, and more people know degrees than radians. But the other way of writing it, radians, where we would put pi over 4 radians instead of 45 degrees, kind of mathematically nicer, but less people are familiar with it. So I did stick the degrees in the short. But as far as the triangle, we don't need to use degrees to define it. We don't need to call it 45-45-90 because this is the only type of triangle that is a right triangle and an isosceles triangle. Isosceles meaning 2 or more of the sides are the same. And to those who are saying they think isosceles means exactly 2, that's actually debated in math. There's been different times in history and different opinions about when isosceles is applied to include equilaterals or not. But we'll say isosceles could be defined as either exactly 2 or at least 2 sides. Either way, the only isosceles right triangle is this one they call the 45-45-90. So this is a kind of classic shape, and we can do a lot with it. We could algebraically get to that root 2 pretty quick if we know the Pythagorean theorem, because, a squared plus b squared should be c squared with that right angle there, so it should be the square root of the sum of those. But what if we didn't want to bust out algebra, or we didn't want to trust the Pythagorean theorem? What if we wanted to see a geometric reason why this logically is true? Well, let's stack a few of these right triangles together. Let's go here, and if I go right here and I cut it in half, this side length was the diagonal. But what if we made a square where that's the side? Well, if I make a square where that's the side of it, if you had your, ruler or whatever and mapped it out, you'd note that you're getting something over here that has exactly 4 of that guy. So when we square that as the side length, we end up with 4 of these little unit guys. Now, the square originally, this square, the smaller one, had 2 of them. So if this square has an area of 1 by 1, and it contains 2 of these, then 4 of these must make an area of 2. And if we have an area of 2 in this, and it's a square, then the side is by definition the square root of the area 2. So we can kind of geometrically see other reasons why it's got to be true that that's the square root of 2. But what if we look at this fella? The square root of 2 was hanging out there. But all of these ones, we're talking about half of that. This half of the square root of 2 was synonymous with 1 over the square root of 2, or the square root of 1/2, or all of these fellas. So then we sort of need to bust out this picture. Now, we're going to start from the opposite end that my short kind of started. We're going to be looking at this side and seeing that here's a 1x1 square. And here we have a diagonal going halfway to the midpoint. And by midpoint, theoretically, there are more than one way we could try and define what the midpoint of a square is. But the most logical one would be that point in the center where these two diagonals would cross. So from the corner to the most logical middle of the square, where those diagonals cross, is half of the whole diagonal. So we know for sure that this little red bit, that half, is the thing we're talking about, half of the square root of 2. So that length also symbolizes the square root of the square root of 1/2, 1 over the square root of 2, and all of those things. And can we get a cool little geometric visualization of why this would work too? Well, why don't we make this, we're going to need to go pretty zoomed in here, but this is the new fellow we're talking about, that little red line. And if we were to, which of these was the pen that worked? Okay, there we go. If we were to make that a side of a square, we could play a kind of similar game and see like what we get. That as a side length of a square has an area of 2 of these guys. And 1 with a side length of a square had a length of 4 of these guys. And if you do a similar backtracking game that we did with that, expanding the diagonal, you can come to various geometric reasons on various scales, because you can always cut these in half and get smaller versions of them. On many different scales, you can come to the conclusion that not only like how we saw the square root of 2 makes sense to be that diagonal, but that half of the square root of 2 also ends up geometrically making sense to be the reciprocal of the square root of 2. And then we're going to go into some algebraic ways of writing it as well that are pretty wild. So looking at some algebraic ways of condensing this, what does it mean in a more algebraic sense, now that we're getting to these like fractional powers and stuff, to have a fractional power or a negative power? Well, if I say something to the power of 1/2, that's the same as referring, for a typical number, don't try and pull these tricks using imaginary numbers or stuff, some of the rules change, but in all the typical scenarios, x to the 1/2 equals the principal square root of x. And so what if I had like x to the 1/3 would be the cube root of x, they're further levels of root. If I had x to the 2/3, that would be the cube root of x squared, because we have like a squared on the x, but then the third makes it the cube root of it. Now if we have a negative, that sends it to the bottom, because x to the -1 in all typical circumstances is 1 over x. So how do we combine these to figure out what's going on here? Well, if we can say that square root can be turned into 1/2, then we get right off the bat this part of the identity, where we could rewrite square root of 1/2 as 1/2 to the power of 1/2. But what's up with this one? 1/4 to the power of 1/4, also equal. We can kind of condense it in a similar way, where if we think of what it means to be to the 1/4 power here, and to have the 4 on the bottom. Well, in general, let's first uncompress this. Let's try and say that instead of saying it's 1/2 then to some power, let's say that 1/2 is 2 to the -1. So we have 2 to the negative 1 to the 1/2. And as you may know, when we interact these guys together, this is going to end up combining into 2 to the power of negative 1/2. So secretly, this is my favorite way of writing it. Square root of 1/2 is a good catchy way of saying it, and this is a good common way of saying it, but this is my favorite way of saying it. 2 to the power of negative 1/2 is this number. This condenses all of that strange info in an interesting way. The fact that we had a square root up there, the fact that we had a whole one on the bottom, all that gets condensed into this fact that the exponent was negative 1/2. So what about what's going on there? Well, if we have a 4 on the bottom, that's like we add 4 to the negative 1 to the power of 1/4. And we can also note that 1/4 power is like a 4th root, and we're going to end up being able to crunch that down and see that it's all this in disguise. And I find it pretty neat to have all these different ways that happen to be the same able to crunch down in a way where it looks like we're just raising 2 to some power, and we kind of are. So sometimes you're going to hit a really weird looking thing that can actually be crunched down even further. As another example, if we had square root of 2 over 4, that's secretly like 2 to the power of 1/2 times 2 to the power of negative 2. Because 2 to the power of negative 2 is a 4th. So then when we combo these, we say it equals 2 to the power of negative 1.5. Negative 3/2, I'll say. So sometimes you'll get a weirdo like that, and way nicer. I mean, mostly you'll see it written like that. But I secretly prefer that way. 2 to the power of negative 3/2. Pretty neat. So that was our little explanation of why some of that short worked. And now I'm going to take a little stroll through some of the comments, chat with you guys for a minute, and then we're actually going to return to a somewhat similar concept, which is these little shapes. Part of the reason I was making such a big deal of what is this little piece like is because they can fit together like puzzle pieces in some interesting ways. And I was just reading about this type of shape, how it can fit into puzzle pieces, how many of them exist on different things recently, compared to a more familiar one to me. The more familiar one are these fellows called pentominoes. Now, pentominoes are a fun puzzle-like thing. And I guess I'll first go through some chat comments and see if I have any little rants to do beforehand. And then return to this, because these pentominoes have a cousin to them that's a different puzzle PC thing made up of isosceles right triangles. So, looking at our wonderful comments, hope everyone is appreciating their Squirrel Appreciation Day. Someone's noting that the 29th root of some number is very close to pi. That's a cool one. I'm a big fan of a simple one to remember, is that the cube root of 31 is surprisingly close to pi. So, like, let me pull it up right here. Let me see. Cube root 31, 3.14138. That's really good. Pi starts 3.1415. So, if you don't need a majillion digits and you just want, you want a little more than 3.14, you want a little more accuracy than that, then go with that cube root of 31. We got some more interesting thoughts about all of these triangles. And someone's joking that they're failing algebra and YouTube suggests them a random channel about math. Well, hopefully, even people who fail the school type of math might enjoy my videos. My videos are not necessarily teaching in the same direction or mood or style that school would teach things. And so I like to think that that is one of my goals, if anything, is to have more people who thought they hated math learn to like certain mathematical things through my videos. So, um, let's see. Somebody's noting some interesting properties of tan of x too. Yeah, there's a lot of interesting properties of that if we're looking at rationals versus irrationals, like they're noting. We may do a little discussion of rationals versus irrationals in a little bit, because if we have square root in our title, you know, the square roots are a very specific, notable type of number that is sort of in a middle level of what real numbers can be. It's a irrational but not transcendental. It's an algebraic irrational. In fact, a square root is known as a quadratic irrational. But maybe we'll go off on that topic in a minute. Thank you all for noting that. Various random comments. Very cool. I haven't done a huge amount of statistics to whoever asked that. And I may do more of that in the future. Statistics can be interesting. It's showed up in random spots during some of my dice-related investigations, for sure. And I do really love certain statistical paradoxes. And by paradox, it just means something that is counterintuitive or seems to go against our, gut feelings understanding. It doesn't have to mean it's false or anything. So there are certain statistical paradoxes that I'm really interested in covering before long. That those will get some episodes about ways that statistics can lead to a somewhat baffling conclusion. Someone's asking how delayed is the stream. If you mean how long until I talk until it shows up for you guys, I think it's like 5 or 10 seconds or something. I'm not sure, but I don't read the chat that often. So it takes like 5 or 10 seconds, I think, for it to be like we're lined up with each other. But I also just spend a while not looking at the chat because these are supposed to be my videos for all of my viewers, and a lot of people can't randomly come when I do my random streams. That's why also I'm going to start putting timestamps, like I said, in the descriptions so that people will know, like, this is the part of the stream where I'm just chatting with my people, and then there will be another part in a minute where it's slightly more concrete knowledge or fun or whatever. Thank you all for the comments. I'm going to return to another topic right now. Keep your eye out for squirrels. I think I'll be able to hear them, but make sure to comment if you see any clues of a squirrel, because it is Squirrel Appreciation Day. Now, in any case, let's talk briefly about one of those interesting things that a comment reminded me of, which is just ideas of what type of number is the square root of 2. So to briefly look at what type of number the square root of 2 is, we first got to imagine we were like cavemen thinking of numbers as piles of items. And then we might just be using integers mostly. And then we may want to at some point start introducing fractions, whether to describe that there's 3.5 of a thing, or to describe that for a given amount, like 1/2 of the people got it, or something like that. We may want to start looking at fractions, which are what's known as the other types of rational numbers. A rational number can include an integer, but really all rational numbers are basically an a over b, where a and b are both integers or whole numbers. Although whole number can mathematically sometimes imply positive and different things. Rational numbers can be negative, but integers on top and bottom. So if we have numbers let's say we want to like look at a number line and we want to zoom in really far on a stretch. So here I'm at 0.01 and here I'm at 0.02. Well, no matter where I go on here, if I want to make somewhere in that zone there be a number I name, any little interval I pick on there, no matter how small, as long as it's an interval of distance, there's any number of fractions or rational numbers that I could invent that live in there. There's in fact an infinite amount in any little interval that has length on this line, an infinite amount of fractions I can pack in there. However, if I were to somehow be able to randomly select one of them from a spot, not an interval, but a point, a single random point out of them, there's essentially a 0% chance that one of them would be a rational number. And that's because although there's an infinite amount of fractions, in between those infinite amount of dots, in a somewhat hard to digest to the human brain way, it can be fully provable and justified that there must be a larger infinity amount of other types of number living between those. Numbers that can't be described in the fractional form. And in fact, it's not super difficult to prove that square root of 2 cannot be a fraction. And we'll do that in an episode at some point. Sometime we'll have an episode about irrationality proofs, where this is sort of level 1, and then something like proving something like e or pi is irrational is a harder task. So square root of 2 is impossible to write as a rational number. So it gets the title an irrational number. But it is the solution to the algebraic equation x squared minus 2 equals 0. Well, it's one of the solutions to that. And so when you're the solution to a finite length little polynomial which has only integer coefficients, then you're called an algebraic number. And so square root of 2 is an algebraic number. The golden ratio, which is 1 plus root 5 all over 2, is an algebraic number. Cube root of 71 is an algebraic number. Things like that that are the roots to a finite length polynomial with integer coefficients are algebraic. And the ones that can't be a fraction like that are the algebraic irrational numbers. So when you see this, you might start to think, well, square root of 2 and its friends are that bigger infinity that was hiding in between there. But not quite. If we tried to put all of those, the infinite amount of algebraic numbers, there is a surreal way I'll go into in a more detail in a video someday of enumerating them, or essentially counting them in a mathematical sense, and listing or plotting all of the algebraic irrationals. And once you've done that and found this way to set up an infinite categorization of all the rationals and all of the algebraic irrationals, you're still left with that being the infinitely small dust in relation to something hiding between it. And the dark space between it, sort of like the dark matter of the real number line, isn't even the numbers like square root of 2. Those are considered a countable infinity by mathematicians, similar to how the rational numbers are. It's the next level, the transcendental numbers, numbers that are irrational and not the root to any finite length integer coefficient polynomial. And those transcendental numbers, which include e and pi, and those may be the only two that you've ever interacted with, turn out to contain the majority of the numbers. They're just hard to figure out how or when to describe. They're like the dark matter hiding on the number line in between this infinitely small in comparison dust of the rational numbers and the algebraic irrationals. Absolutely insane. Now, we can actually go through a justification for why these are different sizes of infinity. But that'll be a whole episode someday. It relates to something called Cantor's diagonalization argument or proof, which is a technique that can actually be used in multiple ways. So if you've seen something about Cantor's diagonalization technique, you may have only seen some of the ways it can be applied. It's an interesting way of taking a list of something that's infinite and showing that it cannot be or can be lined up with what you'd want to call the same type of infinity for a different type of number. Very weird sounding. Sounds like something that you'd never be able to put in a like objective term. But it turns out that there are ways that mathematicians have found to be by far the most logical and somewhat self-consistent and ones that work, ways of describing what an infinity could be. And one of those ways relates to what they call accountable versus uncountable infinity. Although those are slightly more casual names for ones that are typically written with these symbols called aleph null or aleph naught or aleph 1, and there's different ones that are different levels of possibly infinite-esque numbers beyond all of the finite numbers. But that'll be some stories for some full episodes down the line. So, let's see where we're at right now. Thank you all for hanging out and enjoying some geometric insanity with me. I think that our next thing we are going to investigate is going to be me showing you those shapes that look similar to the pentominoes. Now, these aren't something I know as much about, so I'm going to... I mean, the pentominoes are, but the friend of them I know a little less about, so in a moment I'll pull them up on Wikipedia and shrink myself. But these pentominoes have been my friend for a long time. And they're all of the ways that you could connect squares, if you picked 5 squares side by side to each other in shapes on a plane. And my ones are puffed out a unit in the 3rd dimension so that you can try and stack them into 3D things. But you could imagine them flat as well. And they're very fun as puzzle pieces, because although the tetrominoes that you guys may be more familiar with, the Tetris shapes, are called tetrominoes. And wait, if you want a mind blower, dominoes are literally that root. A domino is a 2-mino, just like this is a pentomino. And the one that gets the least credit for some reason is triominoes. You hear about dominoes, you see tetrominoes. I got pentominoes here. Triominoes are getting no credit. And it's probably because there's only 2 possible triominoes. The only possible triominoes are, you got your 3 in a row triomino, and you got your bent triomino. So, those triominoes, someone's got to find some more cool stuff about those that gets them placed in the spotlight, because I've heard a lot more about dominoes, tetrominoes, and pentominoes than these triominoes. But in any case, the pentominoes are marvelous because the tetrominoes can't make that many rectangles. The tetrominoes have this parity thing I've shown in a short that make it impossible to use one of each to make a perfect rectangle. But the pentominoes, there's exactly 12 of them if you count the flips as the same piece. And 12 times 5 units makes 60 total cells, and 60 is such a divisible number, and these things work magic. You can fit them into so many of the dimensions of 60. You can make them into a 3 by 20 or 3 by 20. You can make them into a 4 by 15. You can make them into a 5 by 12. You can make them into a 6 by 10 in many, many ways. But it's kind of challenging. Although there's like so many ways you can do it, It's actually kind of hard. Like I bring them out at parties and stuff, and my friends always try and make a rectangle because they've seen me do it, and it's kind of hard to get all of them in a rectangle. It takes a while of fiddling around with it, even though there's hundreds or thousands of ways of doing it. So these are pentominoes, but there's other ways we could take this concept. And I'm going to shrink my screen for a moment to show you a few. Now, as I shrink my screen, or where are we? One moment. Shrinking myself here. We're going to look at. Well, first I had Squirrel Appreciation Day pulled up because I had to remind all of us it is literally Squirrel Appreciation Day. I'm not making a joke about this. I mean, it's a somewhat silly holiday, but I think it's worth celebrating. Unless you're a farmer whose squirrels ravage your property. I get lucky that the squirrels only eat a few of my fruits. They're spoiled. They have like a buffet. What we're looking at, though, really here, was not Squirrel Appreciation Day yet. Perhaps in a minute we'll look at the front yard to see if there's any squirrels out there. But a polyform is a more generalized idea of, hey, look, they got pentominoes as the picture of it. Classic Wikipedia getting stuff awesomely well. That's exactly the demonstration I would have put of a polyform would be the pentominoes. Now, if you go down here, we see a variety of names of them, and we'll investigate these in a lot of episodes. They're really cool. Like a polycube is the ways you could stack cubes together, and do they form metacubes? What can you do with them? Well, one that we were talking about today were the right isosceles, also known as 45-45-90 triangles. And those are called, turns out, polyabolos, are all of the pentomino-esque shapes you can make with a given number of these. Like with two of them, you can actually make them three ways. You can make them square, that thing, or that thing. And it's kind of cool to see which shapes they recreate, because that one that's a single one is similar, meaning a scaled down, rotated version of that. That is also adds up to a bigger 45-45-90, or as I like to call it, isosceles right triangle. So you get like bigger versions of them as you go on. And you get a lot of strange shapes. And so maybe I'll try and get a set of these someday. Because as I was thinking about the square root of 2 today, I was like, yeah, it reminded me that pentominoes have these friends that do different things. In fact, here on levels 1, 2, and 4, we got a similar version of another isosceles right triangle. So if you want a challenge, try and figure out which levels would we see another possibility for a larger, similar version of that shape. All right. I gotta run inside to grab my charger and go to the bathroom real quick. And I will be back to look at some squirrels and talk some more math with you folks in a minute. I will leave this page open, I guess. Well, actually, no. I'm going to leave the pentomino page open because those are so classic. And maybe you'll learn a little bit about pentominoes. I'll be back in a moment and we'll do a little bit more streaming and try to find a squirrel. For now, leave your thoughts about what you think might be interesting about these, and I'll shrink it so there's more room. What you think might be interesting about these pentominoes. I'll be back soon. Alright, I'm back with the charger. A lot of nice bird song out here. Thank you all for hanging around. Oh, and as usual, I guess I'll need to hope the glare's not too bad if I scoot us a little closer to where the cord can go. Okay. All right, so I'll need to get some more pentomino videos out for you folks soon. They have a lot of fun math behind them. For now, let me regrow myself and then take a peek at our chat, see if anyone's still hanging around here. Maybe we'll try and find a squirrel. I don't know where we're going to go about doing that, but they always love running around on these fences. I wonder if I put out the right type of nut, if I could attract them to want to hang out, if that's good for their diet. I might have to look it up. In any case, let me pull open our chat and see if we got any thoughts to respond to or anything. And we may also do one or two quick bubbles with the bubble gun, but I'll probably wrap up before too long because I want to work on some editing and also may have some plans later. So leave your thoughts or questions now. All right. Well, thank you all. Love you all. Someone mentioning about tiling a plane. It's very interesting to see which ones can or can't. That is one of the things that mathematicians analyze about different polyforms, is which ones are capable of tessellation of a plane or not. So that's quite interesting. As a fun fact related to that mildly, the only 2D regular polygons, so you know, like equilateral triangles and squares and stuff are known as regular polygons because all the angles and sides are the same. The only regular polygons that happen to be able to tile the plane or tessellate it with no gaps are the equilateral triangle, the square, and the hexagon. So those three manage to do it, and it's kind of with the hexagon because hexagons are secretly 6 smaller equilateral triangles in disguise. If we look at the type of polyforms in a future episode that are related to equilateral triangles, we'll notice that on the 6th level we have the option of making a hexagon shape. And on certain other future levels we have the option of making bigger hexagons. Pretty cool. Someone's saying, don't they eat acorns? I think they might, but I don't know if I have an acorn here, so maybe I'll have to buy some acorns at the grocery store. I don't think they actually sell acorns at the grocery store, but who knows? And yeah, squirrels are very cute. As long as they're not like terrorizing your crops, I find them delightful. I think they're tiny, weird, insane, and fun. And someone mentioned that the same 3 are the faces of regular polyhedra. Mostly, and thank you for all the nice thoughts. There is one glitch in that slightly, which is that a dodecahedron is able to make dodecahedrons of the typical platonic solid type. I'm seeing if I can find one around here. Have pentagons for sides. And so pentagon does manage to sneak in. However, the hexagon is sort of where it caps out. So it's sort of like an interesting almost mirror to that, where triangles are really good at wrapping around, squares can wrap around, and those can tessellate. And then you kind of get this like pairing between like that. Pentagons can wrap but not tessellate, and the hexagons are a little more room that makes them be able to tessellate but not wrap. Someone's mentioning 3D tessellation with rhombic dodecahedra, and that would be cool to have a strategy game with cells. I like that thought too. I think I remember hearing that bees of some sorts use rhombic dodecahedra for some of their honeycomb cells. So the fact that certain 3D shapes can tessellate will also show up in evolution of crystals, of insect hives, and various places. So which shapes can tessellate? We're gonna see them in nature some places. Like, if you look really close at a crystal or something, it may have each of its little cells sort of tessellating something for certain types of thing. So quite interesting. Apparently, at some point in history, it was claimed that I forget which of the famous old mathematicians, maybe Aristotle or someone like that, claimed that the regular tetrahedron, like the four-sided die, could tessellate space. And people just believed it for a long time. And then later they checked and they're like, no, there's a little gap. It can't. So, those are some random thoughts. And maybe we will see about launching one or two celebratory bubbles before we depart. And in fact, although we weren't able to catch a squirrel, I mean, not catch, but I mean like catch on camera, I do have a little reminder I can tell you guys about. Squirrels have popped up in the background of main channel combo class videos, and if any of you want an interesting little Easter egg to find, you can look in the episode on the main channel called The Mysterious Hyperdice Sequence. I know for sure that episode has a squirrel in the background somewhere. So if anyone wants to play a squirrel I Spy, you can look there, and I'm pretty sure there's been other squirrels. I just forget whether it was in my shorts or whether it was in any main channel episodes. But anyone who finds any other squirrels in the background of my videos, let me know when those moments were. They could be useful. And there is, luckily, also a squirrel that popped in the background of the last episode I filmed that's not out yet. The episode about base 2i and base i-1 that'll be coming out in a few days, maybe even tomorrow. Tomorrow or the next day, probably I'll have it out. That episode does have a squirrel in the background as well, so keep an eye out for that squirrel. I think I'm going to vanish now. I will catch you guys again in some shape or form later. Another stream quite soon, because it's always fun. I always have various topics I want to share. To anyone who missed some of this stuff, I'll put some timestamps in here in a minute so you can click back and see if there were any parts you want to jump around and watch. And to anybody who wants more Combo Life, make sure you're checking out the main channel for sure. I'll have an episode there soon. And I've been putting out some random shorts on this channel too. And to whoever said that the squirrel was in my shorts, I guess I kind of did set myself up for that. I'm not wearing shorts, but yeah, I was kind of describing squirrels being in my shorts. So that's true. Someone says it's out already. I'm not sure what you mean. Oh, the board game maybe you're talking about? Sounds pretty cool. And yeah, also make sure to check out the cool links here. Like we got our Discord chatting. We got some cool stuff on the subreddit. And we got the Patreon for anyone who wants some bonus stuff. I'll be putting up some more behind the scenes crazy stuff from the past couple of filming sessions on there too soon. And yeah, to whoever came late, I'll put some timestamps in a minute. You can click back and see which parts you want to rewatch. Love you all so much. If you happen to see a squirrel today, remember to appreciate it